Another day, another interview with Umpo, and today Jamie's with a special sort of physicist who doesn't ever use a lab.
Continuing with British Science Week 2021, I'm with Dr. Alessandro Principi, who's a theoretical physicist and lecturer at the University of Manchester. Alessandro, if you'd like to introduce yourself.
Yeah, so I'm a lecturer at the University of Manchester. I'm a theoretical physicist. I'm theoretical condensed matter physicist, to be technical, which means that I study things that are in between the really small and the very large. So, and there is a lot in between. So,
So that leads quite well into our first question, which is, what's your research on, and what does the day in the life of a theoretical physicist look like?
Okay, so my research at the moment is it's on several topics, mostly related to two-dimensional materials. One of the topics is, for example, the study of electronic cooling in graphene. So what happens when, how fast will electron cool down after you hit them with a laser? And this is a theoretical question. So it's also an experimental question, obviously, but it's a theoretical approach, which means that we start from a model, which works very well, and we calculate the resulting observables. Other things that I'm working on are actually also quite always on two-dimensional material, but quite different in the sense that it's related to systems which are magnetic, but they have a strange magnetic order, which is not the conventional ferromagnetism or antiferromagnetism, but it's a quantum order. These are systems that do not order at any temperature. These are called quantum spin liquid, where liquid means that the spins remain free to flip at all temperatures. They never order. However, in spite of looking trivial, actually this system is extremely non-trivial. It's an extreme quantum case in which there is a high degree of entanglement between the spins. So the fact that they not order is not because of trivial temperature effects like in normal magnets, but it's really an effect of quantum mechanics, because the extreme degree of entanglement, extreme degree of superposition of wave function makes it such that they don't, the quantum fluctuations destroy order at all temperature until zero temperature. Of course, this is quite a theoretical problem, but it's also has a relevance for experiments, because there are systems that have this phenomenology, which are very recent and very interesting. A day in the physicist, how this look like depends on, I would say, depends on the stage of your career, whether you're a student, PhD student, postdoc, or a lecturer, member of staff. So this can depend. But let's say there is a certain amount of research you do, which actually decreases over time. It peaks more or less during the PhD postdoc years, and then it decreases over time because you have other commitments like teaching and so on. But in general, it's for a theoretical physicist, actually, it's mostly the research part of the job is mostly doing some calculation, whether with computer or with pen and paper, like in my case.
For a lot of students at sort of secondary school level, this might be the first time that they've heard about condensed matter.
Sure.
In a kind of nutshell, would you be able to kind of summarize as to what it is, what it means, and where they might have encountered it in day-to-day life?
Well, they probably have encountered a lot more than everything else. So condensed matter is this physics that goes from, that is in between, if you want, the very small, that is particle physics or nuclear physics, and the very large, which is astrophysics, astronomy, etc. So there is a lot of stuff in between. So you may have encountered problems, classical problems, even just I don't know. You go to the beach and you see the and you see the water splashing around the rocks and making these rings, and seeing these rings interfere, and you would that's a topic that's fluid. The fluid is an object that can be studied in condensed matter. Fluid doesn't need to be like that. A fluid can be actually what I study is a fluid of electrons, for example, in a material where electrons are free, but in some conditions can behave in the same way, for example. So they can exactly like waves splash around and they hit against impurities and so on and so forth. But certainly you have seen the consequences of condensed matter. Everyone has a smartphone, so a smartphone contains semiconductor chips, and semiconductors are the fact that we have semiconductors and transistors is actually a huge advancement due to both experiments and theory in condensed matter. So this has been it's an important effect. Basically, more or less that you can see with your eyes. It's condensed. I mean, and you can see around you that's more or less condensed matter. So it's I do understand that condensed matter suffers a bit of a PR issue, but I mean it's basically everywhere from your smartphone to your laptop to a fluid to a solid to a magnet. I don't know. Nowadays we have solid state drives, which is another advancement of condensed matter. But we had drives made of magnets, right? So they're magnetized, and there's been a lot of studies in magnetic system and controlling magnetic system with currents in the last 30, 40 years, which have been which have resulted in the technology that we have used since until yesterday. So this is really a very broad field. Not to mention superconductors. You heard superconductors at probably at CERN or in astrophysics, in space related stuff. But actually, superconductors are heavily studied in condensed matter, which is exactly one of the topics of most active topics nowadays. Or you may have heard of quantum computation, which is another branch that kind of connect. It's not exactly condensed matter, but connect closely because, of course, quantum computation requires devices to be performed. And if you require a device, well, this device is as a size that is exactly the typical sizes that you would study in a condensed matter lab. So, yeah, it's very ubiquitous in a way, and overlooked at the same time.
So leading on from that, so why physics, in particular, why theoretical physics, and what first interested you, and what was kind of your path into that? In particular, it's quite a specific area of sort of condensed matter physics.
So. Yeah. Okay. So what brought me into physics as a high school student? Well, okay, I've always been interested in science and math, especially. I always loved math. Science usually tends to be, at least, to be taught in a bit, how can you say, prescriptive way? You know, a set of rules. Whereas I always love math because you can derive stuff, and that's probably why I also like theoretical physics, because you can derive stuff starting from very general principles. And then, of course, I mean, physics has been a kind of a natural, I mean, at least for me, a natural point where to go, because actually kind of combines the beauty of science with the rigor of math. And I think I'm not sure many will share this what I think, but actually the point at school where I really loved the physics was when I did dynamics, because dynamics is a relatively simple topic where you can really understand it, but you can understand it, but you can understand it properly with math. You can show with equations what will happen and understand with equation what will really happen in reality, which I really loved. It's something that I really loved and I really liked so far. So I think it was quite natural that I would end up eventually in some topic in theoretical physics. The way I chose the topic was on what I'm working at the moment was probably fairly random, in the sense that I like some courses, and I asked the professor of this course if I could do the project, the end project with them. And then I stayed in this environment and moved from some postdocs in the related topics and so on, and then end up in this one. I think this is actually, I mean, although it was pretty random, I didn't thought too much what I was doing probably at the moment. I mean, I liked the topic, so I knew what I was doing, but I didn't think too much into the future. This ended up being a quite an active topic of research, where there is actually a lot of research going on, which I didn't know at the time. And this is actually I would say one of the most active branches of physics at the moment, because especially because you have many labs in the world that can do experiments, contrary to other topics where it's more difficult, objectively more difficult to experiments. You have to really push to the extreme. Here you are studying some materials, some properties of some system that you can more or less see and touch. So there is a lot of research going on, both experimentally and therefore theoretically, because the properties that you get are fairly interesting, but they're also quite difficult. That's the quantum speed liquid that I just mentioned.
So what would you recommend to sort of keen to kind of pursue a career in physics? I know that a lot of people might have seen over the last few years, obviously graphene, over the last 10 years, and that might kind of give them a bit of an insight into condensed matter in particular.
Mm-hmm, mm-hmm. So you mean more what to expect, or?
Yes.
Well, what to expect, I would say a lot of study, as you may very well know. I mean, of course, you have to be prepared to study and to also do a certain amount of math and problem solving, which I think it's actually the core, the important bit of doing physics, because you acquire these skills that you can then spend possibly in other fields. So I would say really you have to kind of be willing to study, and to also study hard, and also do math and experiments and so on. So there are certain things.
Is there anything in particular that's your kind of favorite aspect of condensed matter or theoretical physics?
In general, I like the fact that you can, starting from a model, you can derive equations, solve them. Okay, you have to do some approximation to know what to do. Probably it's not so trivial as it sounds, but in the end, you can derive some quantity. You can derive some result, and this result can be experimentally measured. I think this is true for any theoretical physicist. So it's an important aspect of theoretical physics, being able not just to generate theories, but also to be able to generate theories that are falsifiable, so they can be proven experimentally, or proven wrong if in cases. And I think this is actually especially true for condensed matter, where there are experiments. The theory is actually contrary to other branches of physics. For example, I think about high energy. That high energy is actually, I mean, we don't know the final Hamiltonian or final Lagrangian, the final model of the universe. We know we have the standard model, but the standard model may not be the last word. So there are people searching what's beyond the standard model. In the case of condensed matter, the model is pretty much well established. So it's basically a Schrödinger equation. Can be very complicated, but it's basically that's the model. So the problem is you can complicate it quite a bit, and you can get many things out of it. You can get many different behaviors. If you think, basically, this describes many different materials, the behavior of many different materials, many different systems, from metals to insulators to magnets to spin liquids to whatever system you are studying, to superconductors and so on. So there is a huge variety. So that's another aspect that is actually interesting, because being able to not just focus on one aspect, but being able to, with the same tools, let's say, go around and explore many different aspects of the world that you have around. Or I don't have it around. I don't have a piece of graphene on my table, but I know that it exists. I know that someone can measure it. I know that someone can find stuff. Of course, I'm not the one that would measure it for obvious reason. I chose theoretical physics for a reason. But the fact that you can explore all these things, I think it makes condensed matter very interesting, and especially theory, where let's say it's a little less demanding than experiments. In some experiments, you have to really work on an experiment for a long time, and before you get some results out. Whereas in theory, with the same, once you learn the tools, you can apply to many different problems. Of course, you have to relearn. Every time you have to learn something new about the topic you are studying, but at least the tools are the same, so you can roam around and learn many interesting things. So I think that's an aspect of condensed matter physics and theoretical condensed matter physics that I like.
So British Science Week is clearly quite an important year in the calendar for physics outreach. Why in particular do you think that physics outreach is an important thing to do?
I think outreach is in general important for various reasons. Having a more science knowledge in the society is certainly better, because it allows us to understand what's happening. So how to interpret data that come out of the reality, which is more and more complex, in fact. So the reality that surrounds us is very complex, and having the instruments to understand it is a very important, for the future of nations, of societies. I do believe. On the other hand, physics outreach is also important for various reasons, because we have a good pool of students, but sometimes we don't reach all students. There are some very well-known underrepresented categories. Women, for example, this is a very obvious underrepresented category, especially in theoretical physics. You have really very few, although we try to find more of them. It's always hard. And this is clearly a point where outreach can have an impact. So increasing diversity in the university. It's not the only one, of course. There are many, so to say, changes in mentality and so on that have to occur, that are occurring. But certainly, we need to attract people from a background as diverse as possible, because actually, I mean, there is no. I think physics is one of the most. I mean, it should be one of the most diverse possible fields, because to be a good physicist, you just need to be. Or to be a good theoretical physicist, you just need to be rigorous and love what you're doing, and there should be no barrier, and yet there are. So there is certainly underrepresentation for reasons that start very early on. So it's certainly important to do outreach in physics.
Thank you, Alessandro, for speaking with us for British Science Week with UMPO. Thank you.
Yeah, thank you very much for
Thanks for joining us again today. We really hope you enjoyed the interview, and that you will join us tomorrow when we meet Scott Kay, a cosmologist. Don't forget to like and subscribe, and please spread the word to your friends. The hashtag is BSW21, and our social media accounts are @UOM Phys Outreach.